I'm going to talk about work which I collaborated with Alexander Gomilko from Torun and Yuri Tomilov from the Polish Academy of Sciences. And this part of our collaboration started back in 2018, around about the time when I got the invitation to talk in this meeting. So I'm going to cover, in a way, I'm going to cover 4 new functional calculi, but I'm actually really going to concentrate the talk on one of them, speak briefly about 2 others, and then even more briefly about a 4th one. They are all related in various ways. So the first question is, what is a bounded functional calculus for operators? So we have an operator A on a bounded space X. Now, for me, operator generally means unbounded, especially if it's called A. But all the operators that I will have will be closed and densely defined. Some things that I say can be done without the densely defined bit, but it complicate the talk if I have to deal with that. So just assume all the operators are densely defined. And we're really interested in operators A, which are negative generators of bounded semigroups. So suppose we have an operator A, and we have a class of functions which are defined on the spectrum of A. And then suppose we have a way of assigning an operator on X to each function in this class of A. And this assignment should reflect the structure of F, and it also should relate sensibly to A. That's a very vague and imprecise description. Here's something that's closer to being a definition. Often in this topic, the class of functions will actually be an algebra, and in particular, it will be a Banach algebra in some norm, not necessarily a simple norm like L infinity. And the assignment is a bounded algebra homomorphism from that Banach algebra into L of X, that's the space of bounded linear operators on X to X. And it should relate sensibly to A in the sense that if you look at the function Rz of W equals Z plus W to the minus 1, then Rz of A should be equal to the operator Z plus A to the minus 1, and so on. And so when we have all this structure with F as a Banach algebra and a bounded algebra homomorphism, that's what is meant by having a bounded functional calculus for the operator A. Now, if our operator A is a self-adjoint operator on Hilbert space, bounded or unbounded, there's a bounded functional calculus for bounded measurable functions on sigma array on the spectrum due to works of Hilbert and von Neumann a long time ago. If we're not on Hilbert space, that's not so straightforward, and therefore we generally will have to consider functions which are holomorphic on a set containing a sigma of A, and we can define a functional calculus by the Ries-Dunford calculus, where you take a contour integral along a contour gamma around the spectrum of A with the resolvent Z minus A to the minus 1 inside the integral. Now, if your operator A is bounded, this is easily to do. You can take a closed contour gamma around there. If the operator is unbounded, it's more difficult because the spectrum may go off to infinity, and so gamma will have to go off to infinity. But with some other properties at hand, one can make sense of this integral, at least for certain F's and certain A's. Why do we want to have a bounded functional calculus? Well, very often we want to do something which effectively converts an unbounded operator A into some bounded operators. For example, operator semigroups come up that way, where A is typically a differential operator driving some PDE, and we're interested in an associated semigroup, e to the minus TA. So those are in a function of A, and they form a C0 semigroup, provided that these functions of A can be made sense of and have the right properties. Other examples that will be relevant to this talk are A minus 1 or A minus identity to the power n, A plus identity to the minus n, for something called the Cayley transform question. And the third one is the exponential of minus t A inverse, which of course is closely related to the first one, but this comes up for a specific reason. Now, if you're only interested in solving Cauchy type problems, you may only want the exponential functions, but it can have advantages to have more functions. And the advantages are, well, first of all, it's sufficient to have a unified approach to lots of different problems. And secondly, one can hope to get sharper estimates for the norms of the bounded operators that are being defined if you have an efficient way, the right sort of algebra that I talked about. If you make the algebra larger, you therefore introduce more functions f, which may be a good thing, but the ones you introduce may be quite obscure, so that's not a huge advantage. But more typically, the larger the algebra is, the smaller the norm will be, as we'll see as we go along in this talk, and therefore the sharper estimates you get for any bounded operators that you're coming along. And then if you're just doing this from a pure mathematical point of view, it has some aesthetic elegance to describe everything in terms of a single algebra homomorphism rather than a whole family of functions. Now, I'm sure that many of you are aware of sectorial functional calculus, where A is a sectorial operator, and whether or not it's injective is a relevant thing here, but it's a sectorial operator of a certain angle, meaning that its spectrum is contained in a sector of half angle theta, and also you have a resolvent norm estimates. Now, I should mention here, our conventions are that the operator A is on the right half plane. So the spectrum of A is contained in the right half plane of the complex plane. And that means that we'll be working with negative generators. So in a lot of the assumptions statements here, minus A will be a generator of a semigroup. So if we have a sectorial operator, it's possible to define a functional calculus for bounded holomorphic functions on sectors where the sector is big enough, bigger than this angle theta here, and still smaller than pi. Now, you may need the injectivity here to be sure that you can do this for all bounded functions on these sectors. And then you can do it based on a Ries-Dumford integral, which going off to infinity, followed by an extension process. And this procedure was investigated seriously, firstly by McIntosh in the 1980s, and then there's Haas's book from the 2000s on exactly this topic. Now, this doesn't always work, even if A is injective. You can still, if A is injective, you can definitely associate some sort of operator with any bounded holomorphic function on a sector of the right angle, but it may not be a bounded operator. It may just be a closed operator. Quite often, you do get a bounded functional calculus out of this. For many operators A coming from real life differential equations, but it doesn't work for all sectorial operators. I mentioned in passing here that there's a similar procedure where instead of using sectors, you use half planes. So for considering bounded C0 semigroups, a half plane is more natural in some ways than a sector. There's a rather similar process, a re-Stanford integral on a different contour and then an extension process. So now let's suppose that minus A is the generator of a bounded C0 semigroup on some Banach space. And then in some sense, the semigroup should be ET of A, where ET is this exponential function that I had before. That's always been the informal feeling behind the theory of operator semigroups, but it can also be seen as a formal theory. Now, in that case, the Laplace transform of the semigroup, as given by this integral, gives you the resolvent of the operator minus A. And you get this formula. I put in the x's here because one needs to work in the strong operator topology rather than the norm topology usually. Now one can consider a Banach algebra here, which is called LM at this point. And this consists of the Laplace transforms mu hat for measures mu, for bounded measures on mu on R plus. And I'll use M instead of mu hat here. And then M of Z is given by this formula, which looks like a Laplace transform of the measure mu. Therefore, we can define in a natural way, if we replace Z by the operator A, over here it makes sense because we've got e to the minus TA, which is TT. So we can write down this integral as a definition of MA of X now. This integral makes sense, and the operator MA is a bounded operator, and its operator norm is bounded by K, which comes from the boundedness of the semigroup, times the Hiller-Phillips norm of M. Have I written the Hiller-Phillips norm down on the sheet here? Yes, well, this is the definition of the Hiller-Phillips norm of M. It's the norm of mu as a measure. This is fine for some purposes, and the Hiller-Phillips calculus has served semigroup theory very well. This gives a bounded functional calculus on the Banach algebra L of M with the Hiller-Phillips norm. One thing that's not so good about this is that the norm estimate here is often far from sharp. Hiller-Phillips norms of measures tend to be quite large, and we'll see that in a moment later in this talk. Here's a question, the Cayley transform question, which I've already mentioned. Suppose minus A generates a bounded semigroup. Take its Cayley transform, A minus I, A plus I to the minus 1, sometimes called the co-generator of the semigroup, here denoted by V of A. And the question was raised in the year 2000s, I think, round about then, by Gamilko, I think, or at least he was the first person to give a significant answer. We can bring this into the Hiller-Phillips calculus by considering this function here, Fn of Z equals this thing, which is the nth power of something. And these functions are in Lm. In fact, F1 is the Laplace transform of mu, when mu is the measure which is a point mass at the origin minus twice e to the minus t dt. And if I got the things right here, the Hiller-Phillips norm of F1 is 3. Now, because the Hiller-Phillips norm is a Banach algebra norm, that tells us that the Hiller-Phillips norm of Fn is at most 3 to the n. But that's rising rather rapidly and is not a good estimate, because if you put in some more estimate rather than just using the very basic fact that the Hiller-Phillips norm is an algebra norm, you can get the sharp estimate that the Hiller-Phillips norm of Fn's grow like n to the 1/2. It follows from that the VA to the power n do not grow faster than n to the 1/2. But the question that was raised was whether VA is a power-bounded operator, which means that these powers, which is the same as asking whether these powers form, the norms of these powers are bounded sequence. So, but perhaps what comes from the Hiller-Phillips norm is not very good. Perhaps we can do something better. Actually, we can't do something better. It was shown fairly quickly that n to the half was optimal if you allow yourself to work on with arbitrary bounded semigroups on arbitrary Banach spaces. But sometimes, if you put on more assumptions, you can do something better. I'll come back to this question later. So let's go back to the Hiller-Phillips calculus itself, the definition of it. Well, here it is again. M of x is given by this integral. And then we can play a few games, and we end up with a different formula here, which looks more complicated, but it describes M of x with reference only to m and its derivative, and not to the measure mu explicitly. Now, the steps I've done here are informal. The first step is simply uses the fact that the integral from 0 to infinity of tau e to the minus 2 t tau t d tau is equal to 1/4. The second step is because remember that the resolvent is the Laplace transform of the semigroup. And then you can differentiate this and get that the t times tt has Laplace transform equal to the derivative of the resolvent, which is how you get a second power here, minus 2 power coming in here. So then this line is, I've skipped a few pages accidentally. So this equality here is formally, it's using the standard formula for the inverse of a Fourier transform. It's become a Fourier transform because we're just looking at a fixed tau and a vertical line in the plane. The next line depends on Frobenius theorem, and the next line is just observing the fact that the formula for m, you can differentiate through the integral sign and get a formula for m prime, which happens to agree with what's appearing here. So now we have a formula for all these functions m in the Hiller-Phillips algebra. So let's now make this into a definition. Suppose we have an operator with dense domain and spectrum contained in the right half plane, closed right half plane. Suppose we have a function f on the open right half plane and suppose that f of infinity is equal to the limit of f of t as t goes to infinity. Throw in an x and an x star and write down this formula here as a definition of this notation on the left-hand side. So what's in this double integral is just the same formula as before, except with m replaced by f. And then I had, in the previous slide, I put in the assumption that mu of the point 0 should be 0, which was actually used in the first equality here. we have to compensate for that. And we can do that by just throwing in f infinity, which is a complex number, times xx star. Right, now does this double integral make sense? It does make sense if f is in a space called curly B, or if you like, Bezoff type spaces. It could be this notation in some indicating some Bezoff space, but on the complex half plane. And our definition of this space is it's a space of holomorphic functions on C plus, such that this integral of the sup of f primes over vertical lines is finite. So we'll see examples of the space shortly. And then we want to deal with this other part here, and that now is the derivative of this function at a certain point, or minus is, basically. And so we want these functions to have the property that G has here. So they're holomorphic functions on C plus, satisfying this condition. And this is another Bezoff type space. So these spaces are sometimes called spaces of analytic Bezoff functions, for reasons that are slightly peripheral to the main subject. Now, around the turn of the millennium, Gamilko and independently Xi and Feng had come up with the same theorem. If A is a densely defined operator with a spectrum in the right half plane, closed right half plane, and if the resolvents with the x and x star in satisfy the requirements to be in E, then, well, first of all, it's an observation that these integrals must be bounded by some constant depending only on A, and then you get the norm of x and the norm of x star coming in here. That comes from the closed graph theory. And Gamilko and Xi and Feng showed that this condition, these conditions, if you include other things, implies that minus A generates a bounded C0 semigroup. Now that looked the useful part of this result. It's easy to see that if minus A is the generator of a bounded C0 semigroup on a Hilbert space, then this GSF condition holds. So this is necessary and sufficient for generation of a bounded semigroup if you're on Hilbert space. If your operator in A is sectorial of angle less than pi over 2, then GSF holds. And it even holds in operator norm instead of in this weak topology or weak estimation. An operator being sectorial of angle less than pi over 2 is equivalent to minus A generating a bounded holomorphic C0 semigroup. There are examples of generators of bounded semigroups where GFS-SF does not hold. And for example, if you take the generator of the C0 group of shifts on LP of R, where P is not equal to 2, then neither A nor minus A satisfies GSF, although they're both generating actually semigroups of isometries. Now let's think about the properties of this analytic Bezoff algebra curly B, or more complicated notation on the header. If you have a function in there, the function f is always bounded and uniformly continuous, initially on the right half plane, but you can then extend it to the imaginary axis as well. So your function is holomorphic by assumption, it's bounded, so it's in H infinity. The boundary function is also a nice bounded uniformly continuous function on R, or actually the imaginary axis. And moreover, there is a limit of f at infinity as you go to the right. The space is a Banach algebra in this norm here. The integral is just the finite, the integral that determined whether or not f is in B, and this is just the L infinity or H infinity norm coming from the boundedness of f. There is a partial duality between the spaces B and E, which means that if we have a function G in E and a function f in B, we can write down a formula, here it is, which makes sense because of the proper definitions of B and E. This integral is absolutely convergent, and this is clearly bilinear. It's linear in both f and g. One can retrieve the function f in this way. It's this constant f of infinity plus, well, 2 over pi is a factor that comes in, f in duality with the function Rz, which is this resolvent function. So basically this formula is going to make sense, is going to enable us to make sense of f of a. We just replace z by a, basically. Examples of functions which are in this space B. Well, first of all, the Hiller-Phillips algebra, LM, is contained in B, and you get an estimate for the norm here. In the B norm is smaller than twice the HP norm. Next, there's a bunch of functions which are entire functions of exponential type. So if we take a strictly positive number Tor1 and a bigger number Tor2, we can look at the space, often denoted by something like H infinity Tor1, Tor2, which is the space of all functions in H infinity C plus, such that the spectrum, so-called, of the boundary function of f is contained in the interval from Tor1 to Tor2. The spectrum of a function of a real variable is just the support of the distributional inverse Fourier transform of that function. Then these functions, when we think of them as functions of z in C plus, they are entire functions of exponential type, and they're decaying as you go off to the right. They're decaying at an exponential rate relating to Tor1. Now, these spaces are all contained in B, and you get an estimate for their norms in the B sense in terms of the H infinity norm multiplied by something that depends only on Tor1 and Tor2. And it depends logarithmically on Tor1 and Tor2. So this sort of estimate has been discovered in various forms by other people earlier on. I'll come back to that a bit later on. Now we can vary Tor1 and Tor2 here, provided they stays positive, strictly positive. And as Tor1 goes to naught and Tor2 goes to infinity, these spaces get bigger. So we can take their union and then the norm closure of that in B actually gets you essentially the whole of B, except that the function must still vanish at infinity. So this is an important fact in what follows, and it makes the calculus possible to work with. Let's go back to Cayley transforms and look at the function fn of z as before. Remember that the Hiller-Phillips norms of fn grow like n to the half. It's not tremendously difficult to work out that the B norms of fn grow like log n. So this makes the Cayley transform question more interesting, because we're going to find lots of semigroups where this grows at most like log n. Now, I'm also interested in the function e to the minus 1 over z, which is holomorphic and bounded on the right half plane and so on, but it's not in B. How do I know that? Because it's not uniformly continuous near 0. If you shift the z variable, e to the minus 1 over z plus 1, that is in B. Actually, it's in LM. It's in the Hiller-Phillips algebra. Or if you multiply e to the minus 1 over z by z over z plus 1, I think the square is not necessary, but let's leave it in there. This is in B. And in fact, it's in the norm closure of the Hiller-Phillips algebra in B. And finally, for those of you who know what a Bernstein function is, this is a class of functions on the right half plane, or the morphic functions on the right half plane, with certain properties investigated initially by Bernstein. It turns out that if you look at this resolvent, fix a lambda and look at f of, well, there are a few factoring powers in here, and then take the inverse. These functions are in B, which turns out to be useful. Now, suppose that we have an operator A which satisfies GSF. For f and b, we can make this definition of some notation on the left-hand side. And now we know that this gives us an element, fa of x can be interpreted as being a linear function of on the x stars. In other words, as a member of x double star. And the norm of fa is easily seen to be less than or equal to twice. Gamma A was a constant in the GSF condition, and then the Bezoff norm of A. So this is, we hope that this will give us f of A's which map x into x. That's the important thing. We also want it to be an algebra homomorphism, but that's fairly straightforward. So does f of A necessarily map x into x in this situation? First of all, it works if f is in the Hiller-Phillips algebra, and f of A agrees with the Hiller-Phillips functional calculus. That was basically what we established in the 4-line calculation I did earlier on. Can we do it then if f is in these spaces h infinity tor 1, tor 2? Here's where the duality comes in, the duality of E. Because we can consider E deltas, which form some sort of a weak approximate unit. And then the E deltas are also in the Hiller-Phillips algebra. F times E delta is in the Hiller-Phillips algebra. And their limit in the strong operator topology is equal to f of A. This takes some checking and going through things, but it all works. And since the FE deltas all map x into x, and we have this limiting property here, then f of A must also be mapping x into x. Now, finally, this works for all f in B because f minus the constant f infinity is in the norm closure of the union of all these h infinity tor 1, tor 2 spaces. And we got it working for all the spaces in this union. And then because things are nicely bounded, it works on the closure. And then we can just throw in our constant times the identity operator to compensate for the f infinity. And it turns out that this map is a bounded algebra homomorphism from B to L of x, which does the right thing to the resolvent functions. And so we have a bounded functional calculus for A, extending the Hiller-Phillips calculus. We call it the B calculus for A. Some properties Well, first of all, there's an inverse property. Suppose you have an operator whose spectrum is in the closed right half plane, and you happen to know there's a bounded algebra homomorphism from B to L of X doing the right thing to the resolvents, then A satisfies Gromilko-Shih-Feng. So the existence of a bounded B calculus for an operator A is exactly equivalent to the Gromilko-Shih-Feng condition. Also, the homomorphism that you have is the homomorphism that's been defined on the previous slides. It can be shown with a bit of effort that the B calculus is compatible with the sectorial calculus and with the half-plane calculus, in the sense that if you have a function f and you can define f of a in the B calculus and you can define it in sectorial calculus, they agree. And the same for half-plane calculus. Here I go back to mentioning some names of people who did things in this area before. So first of all, there was a paper by Peller in 1982, which considers the discrete version power-bounded operators on Hilbert space. And he showed that the norm of P of t, where P is a polynomial, is less than the constant, depending on the power bound, times the, well, this B is the disk version of the space we've been looking at for the polynomial. Now, in that case, the polynomials are dense in the Banach algebra of analytic Bezoar functions on the disk. So knowing that, you can then extend it to a functional calculus on the analytic Bezoar functions on the disk without any difficulties. An estimate of this form was established by White in 1989. In 2005, Wietze looked at the case where minus A generates a bounded holomorphic semigroup. So that's a sectorial operator of angle less than pi over 2. And she showed that the sectorial functional calculus then produces bounded operators for all f and b. In 2011, Haase produced something similar to what White did, but with rather more functions appearing. And in 2016, Schwenninger did something which improved on varied Wietze's result. And curiously enough, none of Wietze, Haase, Schwenninger cited White. Well, there was a good reason why they didn't cite White, because he was a PhD student in Edinburgh, and he decided before he finished his thesis that he wasn't going to continue in mathematics, so he didn't bother writing anything up, and his PhD supervisor had a policy of not writing papers jointly with one of his own students, so it didn't get published in a journal. And it only came to light, well, in about 2015, the University of Edinburgh decided to start digitizing their PhD thesis from the 1980s and so on. And I think White's got digitized in 2017. And amazingly enough, Yuri Tomarov managed to notice its existence early in 2018. What are the properties? So suppose A satisfies GSF, so there is a calculus. Suppose we've got a sequence in B, which is bounded in the B norm, converges pointwise, and satisfies some side condition. Doesn't look very nice, but it's checkable in reasonable examples. Then F is in B, and you get convergence of Fn of A's to F of A's in the strong operator topology. So there's a slightly neater looking convergence lemma for the sectorial calculus, where you don't have a side condition like this, but you have other things coming in, perhaps, in see Hartz's book, for example, if you want to know about them. Spectral inclusion works. If you have a B calculus and F's in B, then F of sigma A is contained in the spectrum of FA. You don't in general get equality there, but you do get equality there modulo what's happening at infinity if A is sectorial in an angle less than pi over 2. This can be proved by old-fashioned methods which were known to Hiller and Phillips. Let's go back to the Cayley transform question. Now, as Gamilka proved in 2004, if minus A generates a bounded semigroup on the Hilbert space, then the norms of the powers of the Cayley transform of A grow at most logarithmically. Is that optimal for Hilbert spaces? That question I don't have an answer to. But Gamilka showed this in 2004 by ad hoc methods just dealing with these particular functions. The inverse generator problem, this arose in around in the 2000s, or maybe earlier. The function e to the minus 1 over z is not in B because it's not uniformly continuous near 0. I already said that. So we can't apply B calculus to that. We could apply it to this one, but then we've shifted things, which isn't quite right. And we can apply it to this because this is in B. In fact, this is even in LM. If you took away the square, it would not be in LM, but it would still be in B. So using this, we recovered the result of Zwart. In fact, we slightly improved it. And this result says that if A has a bounded inverse and you're on Hilbert space, then for the e to the minus t A inverse, you get some estimate with an absolute constant and a k here and the norm of A inverse, and then a logarithmic term. But it remains unclear exactly what happens in the inverse generator problem. It's known not to work in general, but in Hilbert spaces, it's not quite clear what's happening. But there's a chance we might get closer. Here I put in a theorem which Gamilka and Tomilov proved in 2015, answering a question that had been around for 30 or 40 years. If you have an operator angle less than pi over 2, an F's a Bernstein function, then f of A is also, there's an operator f of A, which is associated with it. And that was known to Bochner. And then this operator is actually sectorial of the same angle or smaller angle. So one can get that from the examples I gave before, and that's why I had the fractional powers alpha and beta in there. Just mentioning something specific to the case of sectorial operators of angle less than pi over 2. Now then the resolvent decays. I think I've miswritten this slightly. I should be, no, this may be all right. No, I think this is probably wrong. But this improved, and this gives us an estimate of MA log MA. The integrand here is slightly wrong. An estimate of this type was found by Wietze, who had, instead of having m log m, she had a constant times m cubed in this result here. But she used throughout dyadic decompositions, Littlewood Paley decompositions, and applied that to show that the functions defined by the sectorial functional calculus were bounded. Now, on the subject of sectorial functional calculus, I come now to the two related calculi for such operators. So there's a class of spaces here indexed by S, which is a real number bigger than -1. You might want to think of S as an integer. Look at the space of functions which are holomorphic on C+, and for which this integral here is finite. Then you can define something. So again, such a function has a limit as you go off to infinity to the right. And then you can write down this formula. So the same sort of formula is true. I haven't written it in the slides, but if you replace A by Z, where Z is a complex number. That needs some working out, but it worked. Then you change the Z to an A and you get this formula, and this formula makes sense under this condition. Now these spaces ds, at least for S bigger than 0, are bigger than B, and they get bigger still as you increase S to a higher number tau. ds is a Banach space in the norm. The norm is just this plus the absolute value of F infinity. The ds is not an algebra, but their union is an algebra, but their union is not a Banach space. The intersection of ds with H infinity is a Banach algebra. And then this formula, it looks as if it depends on S, but it doesn't depend on this, as it turns out. And then it has the required properties of a functional calculus. It gives a bounded algebra homomorphism from ds, or from the union of all the ds's, into L of x, mapping the resolvent to the resolvent. And it has basically similar properties to the B, as convergence lemma and so on. In particular, if we go back to the Cayley transform problem with this function again, these fn's have their norms in any of the ds's for S at least bigger than 0 is a bounded sequence. And that gives a positive answer to the Cayley transform question for bounded holomorphic C0 semigroups. And actually that was first proved by de Laubenfels a long time ago now, but not by these methods. Another interesting thing about the D calculus is that, whoops, lost my place now. If an operator A has a D calculus, then A is sectorial of angle less than pi over 2. There's another calculus also for A's sectorial of angle less than pi over 2. Here we take account of the actual angle, theta, less than pi over 2. And we assume that F is holomorphic in the sector of angle psi, and its derivative is in H1 of sigma psi. This is a Hardy space. If psi is pi over 2, this would be the Hardy space on the right half plane. For psi, which is slightly different, you can more or less guess what the definition of this should be. And then H psi, any function in here is automatically bounded, and H
H psi is a Banach algebra in this norm on F and the H1 norm on F prime. And then using fractional powers, you can convert F to a function G, which is in the ds spaces for all s's. And then you can define FHA to be G D of A to the gamma. Again, this doesn't depend on the choice of psi, which affects the value of gamma. And it defines a bounded functional calculus. And again, it's if there is an H psi calculus for A, then A is sectorial of angle less than psi. So here in H psi, we're looking at functions which are potentially defined on a smaller sector than the half plane. So now I come very briefly to the fourth of these calculi, which is due to Loris Arnold and Christian Lemerdi, who have constructed a Banach algebra of holomorphic functions on C+, so that our B space is continuously included in A, and every operator A, which is the negative generator of a bounded semigroup on Hilbert space, has a bounded A calculus. So they are extending the B calculus to a larger class of functions. So you can consider B in its own norm, you can consider it in the A norm. They're not equivalent norms on B. The A norm is smaller. So potentially the A norm may provide sharper estimates than the B norm. The A norm is defined in terms of Littlewood-Paley decompositions, at least it is in the paper of Arnold and Lemerdi. And that's the only paper I've seen about this. And Littlewood-Paley decompositions are notoriously difficult to provide sharp estimates, at least for people like myself. So it's not clear to me that whether or not this will lead to something, some improvement in the results I've described. And I end finally just by mentioning the location of the main references. 3 papers by myself, Milko, and Tomilov, 2 officially published and 1 officially accepted, and a paper by Arnold and Lemerdi, which you can find in Archive. And so at this point, I stop here. Thank you.
There was, in the late 80s and early 90s, a lot of work carried out by Burks and Gillespie and others using transference methods. Are the results that you obtain at least consistent with the results that they had for things like well-bounded operators and so on?
Well, we haven't investigated that in any detail, if at all. I didn't know that he used to investigate, Burks and Gillespie investigated those areas quite thoroughly. So I can't really answer your question as to whether there is anything in that direction that would improve things further.
There is one question that has been raised about the second last slide. There was a space H1. I think it might be a Hardy space, but would you like to go back and sort of elaborate a little bit further on that, please?
Yeah, it is the Hardy space H1. So, as I said, if you replaced, well, start with H1 of C+. That's defined normally by looking at the L1 norms of the function along vertical lines and letting that tend to the imaginary axis. You can vary it slightly by, instead of taking vertical lines,
take the boundary of sectors where the angle or half angle of the sector tends to pi over 2. You take the L1 norm along those lines. And that agrees with the more common definition on the half plane. Now, if you switch to a sector by doing a change of variable by a fractional pi, you don't quite map those sector things onto sector things. But basically, we're looking at the Hardy space for the sectors, where the L1 function, which is the boundary function, is on the boundary of the sector. And the L1 norms of smaller sectors are smaller than the L1 norms of the boundary function. The literature on that is a bit of a mess, which we've tried to improve in our third paper.